So firstly, thank you very much for inviting me to this seminar series. This is the first time I've given an online seminar, so I'm hoping that the internet will stay okay. But if you see me or see the presentation, just let me know and I will try and fix it. So as Milo said, I'm Mariana Clare. I'm a second-year PhD student at Imperial College London, and I'm also part of the Centre for Doctoral Training for the Mathematics of Planet Earth, which is based jointly at Imperial College London and the university. So my talk today is on the kind of general topic of mathematical modelling of erosion risk in the coastal zone, and specifically about adjoint methods, using them to assess uncertainty in hydro-morphodynamic models. You're welcome to ask any questions, but if you want to talk to me about anything in the presentation afterwards, I've put my email address on the top right-hand corner here to talk to anyone about the adjoint methods or hydro-morphodynamic models. So the general structure of the talk. So in the first part, I'll talk a little and the uncertainty that's associated with them. Then I'll give an overview of adjoint methods, how we derive them and what we use them for. And finally, I'll go over some examples of how we use adjoint methods in particular with hydro-morphodynamic models. So start off with, so what is a hydro-morphodynamic model? So I'm sure most of you know the hydro part is obviously the fluid or the water, and the morphodynamic is sediment transport and bed level, and it's the movements of bed levels due to sediment transport. So we've got this diagram, which basically shows you what a hydro-morphodynamic model is trying to model or is trying to simulate. So you've got flow going from the left-hand side here to the right-hand side. And then you've got two different types of sediment transport. So the first one that I'll speak about is suspended sediment transport. So what happens is, as the flow passes over the bed, if the velocity is high enough, you get erosion. Then the sediment is sort of uplifted into the flow, suspended in the flow, passes along, and then as the velocity slows down somewhere else, it gets deposited. And that, for obvious reasons, tends to be the lighter particles, because they're the ones which are easiest for the flow to pick up. The heavier particles tend to be rolled or hopped along the bed by bedload transport, because they're too heavy to be kind of uplifted into the flow, but obviously they can still move. And both of these types of sediment transport cause bed level changes. Now, throughout this talk, the hydro-morphodynamic model that I'll be using is the one that's detailed in the publication there, which is a publication that I submitted last year. It's available on Earth Archive with the accompanying code, and I will go over some of the details when I give the talk, but it's not really the main focus of the talk. So if you want any more details, you can obviously ask me or go check out in that paper. So why are hydro-morphodynamic models important? So I want to show you a video of a storm which happened in Dawlish in Devon in the UK. So for those of you who don't know, Devon is in the southwest corner of the UK, so it's very exposed to storms coming in from the Atlantic. And for those of you who are UK based, you might remember that there was a lot of storms sort of at the beginning of 2014. And this is the result of one of these storms is what I'm going to show you in this video here. And I think it's pretty explanatory. So here you see some big storm waves within the train line, and this train line was built by the engineer Brunel in the 19th century, so it's an old train line, and so for a reason financially was built on the coast, but obviously that has issues associated with it, including things like this. But that big train that comes towards us is actually running from London through the southwest of the UK. Sorry, there's a message. Oh, sorry. Okay, well, I'll pause the video. The sound's a bit loud. But sorry, so what I was just saying is this is the train line. Was built by Brunel in the 19th century, along the coast for financial reasons, and also it was more easy in terms of engineering, but it's obviously susceptible to big waves hitting it. And this is the main train storm waves. And the best bit about this video is the bit where it's conveniently paused. There's this little windscreen wiper which is doing absolutely nothing, but I guess the driver has got it switched on so that he can see it a little bit easier. But yeah, it's against those huge waves. It would definitely be a horrible train. Sorry. So obviously it causes large scale damage. So this is a photo of basically the same part of the coastline, but after the storm. And you can see that the train line is completely destroyed. And it cost £35 million to fix it, and over 2 months. And intelligently, they built it in this again in 10 years' time, or in 20 years' time, whenever the next really huge storm hits. But for financial reasons and for efficiency reasons, they built it in the same place, which they shouldn't have. But and the other impact, not only did it cost a lot of money to fix, but this is the only train line that links that part of the southwest of the UK with the rest of the United Kingdom. And so sort of not being connected to the rest of the UK cost the Cornish economy £1.2 billion. So there's also huge financial impacts other than sort of the more obvious ones. But it's obviously not just the UK that's affected by coastal storms. So with climate change, sea levels are going to rise and storms are going to increase in strength and frequency. And on this map, you can see the cities where sea level is expected to rise by more than ½ a meter by the 2050s. And it's pretty much most of the major cities, or a lot of the major cities of the world. So you've got London here, but you've also got sort of Mumbai, São Paulo, New York, San Francisco over here. So I'm pretty sure you can name other cities that are on here, but it's a large part of the population which is going to be affected by coastal flooding and coastal erosion. So why are they important? Why don't we just build some huge wall and stop the wave from coming in? Well, I really like this cartoon because I think it's something that we kind of all do. We build a huge structure when there's actually a really easy way to do it. We build some sort of huge code implementation when actually we could have done it by hand in maybe a minute or something. And that's kind of the same thing with coastal. You have a real danger of over-engineering. So you could build a huge massive wall which stops the waves or stops the erosion, but what that does, that might actually have negative impacts downstream. So you might get more erosion downstream. You're also affecting the sediment flow. So there might be areas which are reliant on deposition, which are no longer getting the sand deposits they need. And there might actually have been a simpler, cheaper option anyway, which would have stopped the waves or stopped the erosion, which you hadn't thought about because you've gone straight towards this kind of huge coastal structure. And that's where mathematical models come in, because the only way to know what's going to be the long-term impact of building these structures is by running a mathematical model, putting the structure in and see what happens. So that's why hydro-morphodynamic models are important. So as I promised, talking a little bit about the model and the equations. So the hydrodynamic part of our model is the shallow water equations, because our model is two-dimensional. And the morphodynamic model is made up of two equations. One is a sort of simple bed level change equation, and the other is a sediment equation, which is just an advection diffusion equation where you're conserving sediment. And we solve these equations using Thetis, which is a finite element coastal ocean model developed at Imperial College London in my research group, and there are a couple of other contributors around Europe as well. Within finite element methods, we use a discontinuous Galerkin discretization. So what does that mean? Well, if you know finite elements, so when you are trying to solve finite elements, you construct a mesh on a domain like this one here on the bottom left, and you've got two options. So you can choose for your solution to be continuous across this mesh, which is continuous Galerkin, or you can choose for your solution to be discontinuous along the edges, which unsurprisingly is discontinuous Galerkin. Now, discontinuous Galerkin has several advantages, which I've listed on the slide. Most importantly for us, it's locally mass conservative, which means that the sediment is conserved along the elements, which is really important when you're trying to model sediment transport. That we know of, this is the first use of GG with a full hydro-morphodynamic model. And what do I mean by full? Well, that means that it's got suspended sediment transport in it and bedload transport. So there are a couple of models which exist which just have one and not the other, but that kind of limits their applications, whereas ours can do pretty much any sort of sediment problem you throw at it. Now, that was kind of mostly background, sort of motivation, and like a bit about the model. But what I really want to talk about is adjoint methods. So anyone who works in numerical models will know there's a lot of uncertainty associated with them. So there's two main sources. You have model uncertainty, which can come from, obviously, you have uncertainty in your outputs. There's all sorts of parameters in your model that you need to set, which you might not be very confident on their values. Even things like time step and things like that, you kind of have some uncertainty associated with them. And the other sources of uncertainty tends to be in the input data. So this could come from the fact, if we take the example of coastal erosion, so if you're lucky, someone will come and take a sort of a profile of the beach every 5 years. But that means that if you're within the 5-year period, the data that you're using could be sort of 3 years old and no longer representative of your beach, but you don't know that. Also, the instruments that they've used to kind of measure the profile of the beach could be imprecise, they could be inaccurately calibrated, and that's just for parameters which you can measure. For example, one of the parameters that's important in coastal models is the average size of the sediment. Well, if you've ever sat on a beach in the summer, you look at the sand is not all the same size. And so how do you go about trying to work out what the average size is of that sand? There's a huge amount of uncertainty involved in that. Hydro-morphodynamic models are particularly uncertain again because you've got both the hydrodynamic solver and the morphodynamic solver and the coupling between the two. So you've got lots and lots of places where uncertainty can enter. So how do we go about assessing that uncertainty? So there are a range of methods used. For example, Monte Carlo methods, which I'm sure you've heard of, and ensemble methods. So those are examples of statistical methods. But these are computationally expensive. So to give you an example, So hydro-morphodynamic models themselves are expensive because you're modeling them over a long period of time, you don't want to know for one day, you want to know for 20 years, 30 years, 40 years. And you're modeling over a huge region that you want to know in very precise detail. So I was reading a paper the other day which said that if they'd use Monte Carlo methods with their fairly simple hydro-morphodynamic model, it would take about 4,500 years to complete the simulation, and no one's got time for that. So, these methods are very computationally expensive and simply computationally unfeasible a lot of the time. The other types of methods you have are algorithmic differentiation. So, for example, tangent linear models, which are less computationally expensive because you're not required to run them sort of 20,000 simulations like you are with a Monte Carlo method. But with tangent linear models, you have to run them for each uncertain parameter. And I'll go over that a bit on the next slide. So the method that I really want to talk about is adjoint methods. And so adjoint methods compute the gradients of a model, output functional with respect to some uncertain input parameter that you have. And they are a form of algorithmic differentiation. So for this first bit, adjoint methods, the derivation for adjoint methods and the derivation for tangent linear models are the same, but then I'll show you where they differ and where adjoint methods can be better. So let's first consider our model, where U here is the solution and M is some uncertain field or parameter. So the first thing we do is we differentiate with respect to the uncertain parameter, just using the chain rule. And then we substitute this left-hand equation here into the right-hand equation. And now this is where tangent linear models differ. So if you have a tangent linear model, what you're trying to calculate is this product here, which you can see is dependent on the number of parameters, M. So like this is why I said, if you have a tangent linear model, you need to run it for each parameter that you're uncertain about. For the adjoint problem, what we do is we try and calculate, we solve this equation here, which is, you can see displayed below. So the key thing to note about this equation is that it's not dependent on M. So it only requires you to, if you have, let's say I have a million independent parameters M, sorry, let's say I have a million parameters M, then I still only need to solve this equation once. And if I have one, I only have to solve it once. So that's great. If you're a numerical analyst and you're saying you only need to run your model one time, that's great for computational sort of efficiency. But you'll notice that this equation is much more difficult to formulate and to solve than, let's say, the tangent linear model, which is up here. So that's why traditionally people have used tangent linear models rather than adjoint methods. And once you have the solution to this adjoint equation, you can find the derivative. So what are the advantages of an adjoint method? Well, I've kind of gone over some of these just now. So you're increasing the number of uncertain parameters has no effect. And also significantly, no assumptions are made about the distribution of the input parameters or outputs. So that's something, for example, in Monte Carlo methods, you might have some sort of statistical distribution and you assume that your parameter varies in some sort of normal distribution or exponential, something like that. But with adjoint methods, you don't have that. Sorry, I'm just gonna. But as I've mentioned, adjoint equations are difficult to derive by hand and implement computationally. So that's where, but that's where we have an advantage. So within Thetis, there's this flexible, free to use pyadjoint module, which allows you to generate the adjoint equations automatically. Now, I don't take credit for this at all. It was developed by Patrick Farrell and Simon Funke, and the paper there is in the reference. What we have done as part of this work is we've developed the ability to derive the adjoint of a coupled model. So in our model, we've got the coupling between the hydrodynamics and the morphodynamics. And as I'm sure you can imagine, that can be a little tricky. So that's the sort of added functionality that we've added in, but most of it was already there. So okay, so we've derived the adjoint method, but what can we use it for? Well, the sort of application that I'm most interested in is using it to solve a minimization problem. So you have some sort of functional J that you want to minimize, and you subject to the sort of it being a solution to the model equations. And hence, so then you can find the value of M, which minimizes the functional. The other application is you can use it to do sensitivity analysis. So you find the model sensitivity to a given parameter M. So if we go back to a coastal example, for example, let's say you want to know if I build, where would be the best place to build the wall, which would, build a coastal wall to stop waves coming in, which would have the least impact on the surrounding environment. And that then you would look for, you would sort of get a sensitivity analysis map, and you would look for the best place that you could locate it without causing sort of damage downstream. So if you want to do model calibration, the output functional has this sort of general form. So the first part, I think, is pretty obvious. You're just trying to minimize the difference between your model output and the true value. This second part, if you do sort of image processing or image analysis, you might recognize it. So this is just a regularization term which kind of tries to reduce noise and enforce smoothness. So there's lots that you can use. The standard one, I think in most fields, is the Tikhonov regularization term, which is what you're seeing here. but there's no reason you couldn't use something else. So the problem is though, what is the true value? So you could have the true value from the real world data. Let's say you run an experiment and you have the output from some physical experiment. But that's kind of difficult because the whole point is that you don't know what your parameter is. So you could run your adjoint method, you could minimize your functional, and then you come up with some value for m, but you don't really know whether that's right or wrong, because the whole point was that you didn't know what it was to start off with. You can see if it's like physically okay, but it's difficult. So the other tool that we use sort of as a verification tool is something called a twin experiment. So what you do is you run your model once with a known value that, for example, let's say you pick alpha is 1. I don't know what alpha is, I'm just picking an example. And then you take your output and you make this the true value. And then you run the model again without the knowledge of this output or what the input parameter was. And you use your adjoint method to optimize your output functional, or minimize your output functional and find the optimal parameter m. And because you know what the true value is, when your adjoint method spits you out alpha equals 1, then you're like, oh yes, it must have worked. And that just helps you verify. And then you can be confident that when you go to your real world experiment, the value that's coming out of it is a correct value. So far it's been kind of theory and quite dry. So I'm hoping now we get some examples and see how it's actually applied. So the test case I'm going to be looking at is this test case of a migrating trench. So what you can see in the video is the bed level, and over time it's changing. So you've got a trench which starts off, and then the trench migrates across the screen with suspended sediment and bed load transport. And the reason why I picked this test case is that it's fairly simple, but it's also very sensitive to parameter changes, which you'll see in a second, in a couple of slides. But perhaps the kind of most important thing is that this test case was used as an experiment in the 1980s by Van Rijn and co. And so I actually have experimental data, and so I can do real world calibration for this test case. Which is obviously really what we want to be doing with an adjoint method. So what are some model parameters that we're uncertain about? So here we have the diffusivity constant. So this just controls the amount that the sediment diffuses through the flow. You might remember I said the sediment concentration equation was an advection diffusion equation, basically. And you can see here in this plot that changing the diffusion constant changes the output result by quite a bit. And if you're just looking at it, you'd be like, okay, probably 0.15 is the best approximation to the experimental data. But someone else might look at it and say, 0.2 doesn't look too bad. So you want something a bit more rigorous than that. Some other important parameters. So you've also got the input sediment rate. So that's how much sediment is coming into your system. So you can imagine on a beach, that's kind of impossible to try and measure how much sand is hitting your beach every day. Another important parameter is the reference height, which basically just controls the amount of friction between the bed and the flow. And finally, we have a sort of numerical parameter, which is this slope effect, which basically controls the gradient of the slope and works a bit like a slope limiter. So it's an example of sort of uncertainty in a model, rather the other two are sort of uncertainty in input data that you could try and record in some way. So here's our first example. So this is a twin experiment. So remember, this means that we know what the real value is. And on the left, you can see that the output functional reduces as it's being kind of optimized. And more importantly, on the right, you can see that the difference between the value that's coming out of the adjoint method and the true value that we know what it is also decreasing. And you can see that, so by the time we get to the 6th iteration, the error is 10 to the minus 5. So the adjoint method has done a really good job in minimizing the output functional and giving us the true value for this model. Now, I said that one of the advantages of an adjoint method was that we could use it to do multiple parameters all at once. So here we have a kind of very fake problem of a sediment wave hitting the trench. And what we're doing is we're recording the bed level after every couple of time steps. And then we're feeding that as our true value into the model again. And we see that the functional reduces as the number of iterations increases, which is great. And here, obviously, we've had to use a regularization term just to keep the kind of output smooth. And on the right, you can see the model value and the true value. So I think it's a pretty good approximation. And importantly, because the error is reducing at each iteration, if you were to allow the optimization algorithm to take more iterations, then you would probably get an even better approximation between the model and true value. So at the moment, I guess the true value has got a slightly higher value of sediment concentration at the top of the bump, but it's still doing a pretty good job, considering it has no knowledge of what the true value should be. So we're kind of satisfied with our twin experiments. So now we can move on to doing calibration with real data. So this is using the data from the experiment that I was mentioning from the 1980s. And you can see again that the output functional decreases. And importantly, you can see that the optimum value of the diffusivity constant is clearly converging to a value. Now, remember when we looked at the graph, it kind of looked a bit like 0.15, and the value that the algorithm is converging to is about 0.16. So that seems physically sensible, and it seems like our algorithm is doing the right thing. So if we use that value of 0.16, this is what the comparison between the experimental data and the bed level looks like. So it's done a pretty reasonably good job. Where it's failed, where it's not done so well, is sort of this bit here, where I have several theories for this. I think it might be because there's too much sediment entering. So that's what, like I said before, input sediment is a big uncertainty. So I'd like to calibrate for that. But we can also look at calibration for other parameters which might improve it. So this is for the friction. So we can see again, the functional is reducing, the KS is converging, although it seems, so the value that we started with before was 0.025 and it's converging to 0.02465. So the difference is not massive. So probably actually our guess of 0.025 or our measurement was pretty good for this one. If we take the slope effect parameter, so that's governing the gradient of the slope, again, the functional is decreasing, and again, the beta is converging. And here, actually, the beta is quite significantly different to what our previous guess was. So we guessed before 1.3, and now it's double that, it's 2.6. Yeah, so but it's still physically reasonable to have 2.6, but obviously it's quite different to our initial guess. So this is what the bed level looks like with those 3 optimum parameters. So we've still got the problem on the slope, but as I say, I think the main problem is coming from the input sediment. So that's something that I want to look into. And there's other parameters that can be calibrated for as well. So it's still work in progress, but it shows that at least the adjoint methods can be used for this sort of thing. So to summarize, so I hope I've convinced you that hydro-morphodynamical models are important, and they're an important area of research to mitigate the effects of coastal flooding and erosion. And I hope I've convinced you also that adjoint methods are a good way to assess this uncertainty. And although you didn't see any of the code, that it is very simple to implement using pyadjoint. And that reference that I included earlier is a good place to go and look at how you might go about doing it. And finally, I think I've shown that adjoint methods can be combined with these hydro-morphodynamic models to accurately calibrate parameters, including from real-world data, which is really where the key is. So I'm doing a PhD, there's always more work to be done. So as I mentioned several times now, I want to conduct further parameter calibration, particularly the sediment rate, which I think could be really interesting. I also would like to use the adjoint method to conduct a sensitivity analysis for some of the parameters, particularly friction, tends to be a very useful parameter to look at, because some areas of the bed, the friction in some areas of the bed can be more significant than in other areas. And finally, you may have noticed that I talked a lot about coasts, but then the test case that I showed you was a trench that was very much not near a beach. So I'd like to apply it to a coastal test case. And what is particularly interesting is that is using an adjoint method for historical tsunamis. So there are, luckily there aren't that many tsunamis every year, but sort of when you look across the historical timeline, there are lots of tsunamis. But we have no records. Nobody was out there with a gauge in the ocean sort of trying to measure velocities or anything like that. So there's so much uncertainty in input data. Normally the only things that you have are sediment records of sort of sediment that was deposited as a result of a tsunami. So I've been working a little bit with some people who are looking into the 1755 tsunami in Lisbon. And I've been talking to them, and they're very excited about the prospect of using an adjoint method to try and find some of these parameters that have been historically uncertain, and try and use an adjoint method so that we can have a better idea of what they are, what these parameters are, but also have a better understanding of the tsunami, so that next time when there is another earthquake, which I think is overdue, they'll be able to kind of know how to protect against that tsunami, or at least better protect against that tsunami than if they didn't have that knowledge. So it's not just coastal flooding from storms that we need to worry about, it's also from tsunamis. So on that very positive note, I'd like to invite any questions, and here are some references if anybody's interested.